So, in my last podcast on physics, I mentioned that life is an illusion. And I just want to go into that a little further because these are just my thoughts. No, as far as I know, no physicist, not even Einstein, came out and said life's an illusion. But here's why I say it. And I'm going to discuss some physics with you, very little math. But Einstein is fundamentally based on Einstein's, he had the special theory of relativity and the general theory of relativity. We've discussed the special theory of relativity. That's E equals mc squared. The significance of that is that it shows that there is a mathematical relationship between matter and energy. Now, first postulate of that is that energy cannot be created or destroyed. That means there's a finite amount of energy in the universe, which goes back to the Big Bang, which I said I would discuss later, but I'm not going to do it today. So there's a finite amount of energy. It can't be created, it can't be destroyed, but it can be manipulated and put into shapes and forms which we perceive as solids. But as you tear this apart and get deeper and deeper and smaller, when you take the molecules out, and then you take the molecules apart, you find atoms, you take the atoms apart, you find neutrons and electrons, and maybe some positrons in there, and neutrons. And you say, well, I keep, taking this thing out of the box, right? And every time I do, there's another box in there and smaller and smaller. And then you start getting into quantum mechanics, and you're finding out that there's energy associated with certain levels of electrons, and there are various realms in which they move around. And there are discrete paths that these people have, that these electrons follow, and there's limitations lower and higher in each energy shell, we call it. It's actually like a racetrack, and there's no continuum on the energy of electrons. As they move from shell to shell, they give up a discrete amount of energy, a quantum. That's where quantum mechanics comes from. But what we find is that as we get smaller and smaller and smaller into these things, they more and more resemble waves as opposed to solid particles. And you've got bosons and mu mesons and all kinds of quarks. And these things appear not to be solid. So the question is, well, how do you build a human body, for example, which is solid, or a house or anything else? Let's take a house. So how do you take a brick that's made of intangible things that you can't hold, because you can't hold energy in your hand, it doesn't have any mass yet, and yet it can be converted into mass by the way in which it's arranged. So you've got this stuff that you can't hold, and somehow you're able to play around with something that you can manipulate with magnetic fields, for example, but you can't physically hold it, and you're able to manipulate it in such a way that it becomes a brick. And then you put a whole bunch of bricks together, you have a solid wall, and you think, wow, life is solid. But the reality is it isn't, because it's made up of a bunch of things that aren't solid, because energy is not solid, and all these things are just made up of energy. And so now let's talk about we just talked about the special theory of relativity. Now let's talk about the general theory of relativity. And without going into detail, it's a very complicated formula. It looks small, but when you expand it out to the universe, it's very big. But remember, Newton's theory of gravity is equal to a constant g times m1, m2 divided by r. m1 and m2 are the masses of the two bodies who have a gravitational attraction for each other. So when we drop something and it falls to the ground is pulling it down, but this thing we dropped is also pulling the Earth up. It's so small that you can't measure anything, so we got things pulling the Earth up all over the planet, and they have no impact at all. But you know what does have an impact on the Earth? The moon. And how do you know that? Go down to the ocean, go to the beach. Don't go in. Sharks in there. Just go down and watch it. And when there's a full moon, guess what the ocean does? It comes up. When the moon's on the other side, it pulls it down. So that's one of the things that causes the tides. The gravitational attraction that the moon has on the Earth, and in particular, the least dense part of the Earth, which is the ocean, and it pulls that ocean up toward it, and voila, we have high tides. So now let's talk about light. So light is what? Is light a solid? So I have a very dear cousin of mine. She's a very, very smart, very savvy woman. She works for a scientific magazine, very interested in science. And so we were having a few bubs and a few brews in an English pub. And she says, so tell me, Cousin Eddie, just curious, I'm not an active physicist, but I have the credential. And she said, well, tell me, you're a physicist. Can you tell me what light is? And I'm like, I gotta have another drink. And this time I had a Guinness, because she asked a question that was really annoying, because I said, you're asking me a question that physicists and learned gentlemen have been trying to figure out for centuries, and thousands, not centuries, for thousands and thousands of years. Cavemen were struggling with this problem, and I know because I grew up in a cave. So I'm older than I look. So I says, you're asking an impossible question. What we know about light is it has characteristics, and it has a constant speed in a vacuum. You can slow light down if you're running through a crystal or through that's what a rainbow is, when the light is slowed down and it breaks into its constituent parts, and you can see all the different colors of the rainbow. White light is the combination of all those different colors. So you can slow light down and make it bend and so on and so forth, but its speed in a vacuum is a constant, and it's the maximum speed at which anything can move. I don't think anything can move at that speed. You can move it just below it. So I said it acts like a wave in that it has wave characteristics, and also it acts like a particle. It has particle characteristics. And I didn't go into some of the experiments like the slit experiment, but we wrestle with this, and you measure light in photons. But light's not a tangible thing. You can't hold it. You can simply measure things that it does and the way it behaves. And so Einstein's proof of that was, because he said light would be subject to gravitational forces. If it is, that means that something which is intangible, you can't hold it, you can't push it, it doesn't have mass. Light doesn't have mass. But Einstein predicted, because he was smart. And incidentally, there's a movie out about Einstein on Netflix, which I just saw, and it's a great movie. I loved Einstein not just because he was largely responsible for my career path in life, but also because he was a good man. And it's largely about Einstein during the early days of Nazi occupation of Germany. But he was an amazing person and a good person, a good-hearted person, and pretty smart. So old Albert figured out that light would be subject to the force of gravity. Well, how are you going to determine that? Well, the answer, of course, you're very intelligent, or you wouldn't be watching this cast, is not to take a flashlight and shine it and see if the beam bends down toward the Earth. If you think that's an experiment that's worth doing, then you're a moron and you shouldn't be watching this program. And how do I know? Because I've tried it and it didn't work. So the only way you could ever do that is you have to have an interplanetary experiment. And how are you going to do an interplanetary experiment when in those days we didn't even have the population of Mars that we have today? And of course, we didn't have anybody on the moon, and now it's heavily populated, mainly with undesirables. And no, I didn't put all the Republicans on the moon, for crying out loud. Anyway, you have to excuse, I have people in the background who are saying annoying things to me all the time. Oh, actually, they're just in my head. But why do we have to talk about that now? My psychiatric state is not what we're discussing. So how are you going to do this experiment in outer space if we're not in outer space, other than figuratively? So he says, well, there are planets all around there, and they emit light. Now, the sun is the only planet that emits light, but everything we see because sunshine comes down, or now artificial light, bounces off of whatever we're looking at and pops back into our eyes, and that's how we see things. So what Einstein said was, look, there are planets that we know are behind the sun. And I don't know how we know that, but we know it. But you can't see them. But he says, if my theory is correct, the light that is reflected off of the celestial bodies and heads back toward us, we'd be able to see that light. Because what happens is the light from the planet from the back goes scatters out in all directions. And as the light waves come toward the sun, if they come straight to the sun, they bounce off. If they're not going straight to the sun and they're going straight out that way, they're not coming to Earth. So how could we see them? And here's the answer. What happened to that music that I'll do it without the music. Here's the answer. So, according to Einstein, light waves are subject to the force of gravity. So here's the Earth, here's the sun, and behind the sun, over here, is this planet. Or it could be a star. Maybe it was a star. I don't remember. Star or planet. Whatever it was back here. I think it was a star. Anyway, whatever it was, we wouldn't be able to ever see it because its rays, its light rays, whether they're bounced or whether they originate, would go straight to the sun. And since this planet or sun or whatever it is smaller than the sun, its light rays would be blocked before they could get to us, so we'd never be able to see it. There's only one way that you could see that, and that would be as if the light rays reflecting off of this body back there that's over here. No, that's the sun. It's over here. Those light rays reflecting over here. What am I, a hula dancer? That those light rays, as they head out into space, so that we wouldn't see them because they're going out this way and they're going out this way, and we're over here, and the sun's back here, and these rays are going out here, we'd never see them. Unless those rays were pulled toward the sun. My physics teacher used to talk about that. That's why I do. My physics teacher in high school, who was probably the best physics teacher I had, even though we didn't even use calculus. So, these are the light rays shooting out. Here's the sun. Here's let's say my head is the Earth. No, please, I don't need those kind of comments. I'm very sensitive about my head. So, here's the Earth. Yes, I know, it means I imagined it, which is really what this is all about. Here's the Earth, here's the sun, here's that planet back here, and these are its rays. If Einstein is correct, as those rays shoot out, the sun's gravitational pull will pull these rays toward it. Theoretically, the light waves would also pull the sun. But here you have something which is not a solid object, right? Light's not a solid object. Light acts as though it were a solid, as though it had mass, because remember, gravitational force is dependent on mass. So mass is what we think of as a solid. So here's the sun, here's the light rays shooting out like this. As it gets to the sun, as it gets closer to the sun, it's pulled into the sun's gravitational field. Not straight in, because it's moving, it has velocity, it's going this way. It curves around the sun, and it's right toward my head, the Earth. which means we can see it because we see things by reflected light. We can see this planet because its rays of light are bending around the sun and coming straight at us. When we look in the sky, we see this planet. Do we see it behind the sun? No, because we can't see through the sun. We see the light rays coming to us from the side of the sun as the light rays curve around the sun, so it looks to us as though this planet or star, whatever the hell it is actually to the right of the sun. We think if you're just looking at the sky and you're not Albert Einstein, you look at that and you say, oh yeah, that's the Gazuna Heart, whatever it is, planet or sun. I'm not sure which one it was. I should look that up before I get on this thing to talk to you. But whatever it was, it doesn't matter. It's something that we can see by its reflected light, and since the reflected light goes around the sun and comes at us, if we take a ruler and we extrapolate and we just take the path that we see coming toward us and say, so that it has to originate on a straight line from us, it's right there next to the sun, and that's where it sits, and that's where it lives, and that's where it originates, and that's how we know where it is. But we know that it doesn't live there. We know, I don't know how we know it. We know that it's not there. It's behind the sun. So the thing that's behind the sun is visible to us, but we view it as though it were to the side of the sun because its light waves curve around the sun because of the force of gravity. And that's how we know that that light is subject to the force of gravity. Einstein figured that whole thing out, and it wasn't until many years later that somebody actually was able to do that. There were people, because you can only do it, I forgot this, interesting fact, you can only do it when there's a total eclipse of the sun. That's the only time you could do this. So there were people running around the world trying to set up apparatus to view this star, I'm going to call it a star, to see this star during a solar eclipse. And they have to find the solar eclipse, and they have to go to all parts of the planet to find the place where they could see a solar eclipse. And every time they tried, something happened, there'd be fog, and they wouldn't be able to see this thing. So this went on for years. And finally, someone actually did it. And they actually were able to see that what Einstein predicted was totally true, not only as to the star appearing to be to the right of the sun, but exactly how far away from the sun it appeared to be. How this guy came up with it, it's just amazing to me. So that's how we know that Einstein was right, as he was about almost everything. He was correct, and all the people who said, "How can you say light has mass? You can't. Here's a light beam coming at you. You grab, try to grab. You could have nothing you can grab, push, pull, hold on to, and yet it has mass." So how do you explain that? Well, I don't. Nobody has ever explained it. But one kind of theory in my head is that if mass is nothing more than an ordered stream of energy, then energy, as we see it in photons of light, actually has some characteristics of mass, and that's how they define light today. Its characteristics, it's a phenomenon which has characteristics of mass and characteristics of waves, which are not mass. When the ocean is going up and down like that, it's not moving, it's just vibrating. Some of that gives rise to string theory, which I'm going to give you a break and not discuss string theory today. But Einstein established theoretically, and then it was later established through experiments, that light has mass because it's subject to the gravitational force. So this was phenomenal. It just seems incoherent that you would think that a table has mass. We don't have a problem with that. But to think of a light beam having mass, remember that song I sang earlier when the neighbors called the cops? How do you solve a problem like Maria? And the last verse is, how do you hold a moonbeam in your hand? Well, you could extrapolate that further and say, how do you hold any light beam in your hands? Not just a moonbeam, but any beam. You can't hold light in your hand. I'm sorry, Maria. You just can't do it. That's right. Yeah. That nun was an early day physicist. So anyway, the nun that sang the song, that's the nun I'm talking about. Don't ask stupid questions. So that triggers in my mind the thought that, well, when you look at what light does, that light has these characteristics of mass and energy, and neither one being clearly defined. And we know that we can get, as we get smaller and smaller, the more we have to discuss the elementary particles, as Feynman called them in his book, which I recommend to those of you with the physics background, is that matter disappears. And what do we call something that looks like it's a solid, but when we walk up to it to drink the water and take the fruit from the palm trees, it doesn't exist. It's called a mirage. And mirages are real things. So just think about, think about what how weird a mirage is. It looks like it's really water and whatever there. A lot of it, fueled by the imagination of a person who hasn't had anything to drink. And, well, since they closed the bar the night before. I get it, never mind. So, I like that one. That's my best joke ever. And it's not even a joke. It's true. Scientific studies have shown that most people who see mirages are drunk. So, but there is such a thing as a mirage. It's not real. It's not physical. It's not tangible, but it appears to be. And basically, everything we have around us is not made from solids at all. It's made from ordered states of energy. And when you burn something, the order goes away and we have energy. When you blow up an atom bomb, the plutonium shrinks and what's released is energy. It's converted into pure energy. Theoretically, you could take that energy, and if you could do it, theoretically, you could take that energy back, recombine it, and recreate the plutonium atom. So you can create life. Those things being true, and everything I've said there is true, except the part about having to be drunk to see a mirage. What other conclusion can you reach but that we don't really live in a world of solids? We live in a world of energy. So basically, you could reconvert everything that we see around us back into just raw energy, and it wouldn't occupy any. It doesn't. It's not tangible, so it doesn't occupy any space. Doesn't have any weight. It's just out there, and it's constant. And it's like, to me, that's the secret of the universe. That explains where we came from, why we're here, how the states got ordered in the way that they are. Well, you're going to have to ask God that, which is one of the reasons that Einstein was a firm believer in God, and so am I. And I also don't believe that people disappear once they die. And reality is, they do disappear because we can't see them anymore, but that doesn't mean they cease to exist. Because part of, and I talked about the fish the other day that I saw die, and you could see the life going out of it, and it was changing colors. When we die, unless we're somehow preserved, our body disintegrates. It just goes away. What's left? Well, energy. And when we have the energy within us, we call it soul. That allows the molecules in our body to be organized, the energy in our body to be organized in the way that gives us our appearance. But it's not real. What's real is what's inside of us that converts the energy and orders the energy so that we appear to be a certain way, and then this energy that we've converted into appearance of a solid then can control what this solid does. Yeah, I know there are some people who are not all that solid, but we're not going to be here to brag on fat people. So, and if you're fat, I don't mean any. What's the politically correct way of saying fat anymore? When you find out, let me know, because I don't want to insult anybody. Okay, I like insulting people, but that's me. That's my weakness. That's a fault of my energy. Yeah, it's not my fault. It's the energy's fault. But in all seriousness, we are an ordered state of energy. Every one of you watching this is nothing more than energy. And when you die, that's all this order of the energy just goes away because the energy is gone, and so the body just crumbles. Even bones eventually. It just crumbles and disappears. And that's true of every living organism. So this weird thing is that the what orders, whatever the phenomena that orders life is also the phenomena that allows the life to leave, but it doesn't disappear because energy, the total amount of energy, is fixed. It's a constant. We come in, we go out. We come in, we go out. So, what happens to us after we die? What happens to this energy? Are we all part of one big mass of energy, or is our energy discrete and individual? You have to think that it is, but now I'm way above my pay grade. So I'm just putting these things out to you because they're interesting to me, and hopefully they're of some interest to you. But that's. And I just want to say this. This is Sunday, so I'm feeling very religious. But the reality is, Einstein was very religious, even though he didn't believe in any organized religion. And I think that's probably true of me too. Even though I was an altar boy, I don't believe in organized religion, but I do think religion has its place. I'm mellowing somewhat on my views about religion. It's just religion depends upon who's religious and what they're doing with it, like most things. So ignore me when I go off on these because my mind flips around to different topics, and I apologize for that. So the central topic here is that life really is an illusion because everything we think is a form, is a reality, isn't. And I think this is consistent with the Plato's Republic, which is really about Socrates and the world of the forms. I think he was ahead of his time. Yeah, I do. So read that. Also, if you're having trouble sleeping, I recommend the Phaedo, also by Plato, again about Socrates. And I used to keep that by my bedside and read it every night. I don't know what happened to it. Probably it disappeared because it was just a mirage. Anyway, on that lovely thought, I'll wish you a happy Sunday. I'm sorry there's no football today. We're just going to have to tough it out. In the meantime, you can watch these podcasts. Yeah, how's that as a substitute for football? Yeah, okay, well, I tried.